3 mission standardizes the architecture.
Each launch is about learning more about what's needed.
总的目标是2030年前。
We cannot lose the moon and lose the race to the moon to China.
中国无意和任何国家搞太空竞赛，我们也不谋求所谓的太空优势。
If we fall behind, if we make a mistake, we may never catch up, and the consequences could shift the balance of power here on Earth.
We will not only plant our flag and leave our footprint, we will establish a foundation for an eventual mission to Mars, and perhaps someday to many worlds beyond.
Right now, something is being built above our heads and on the lunar South Pole, and most of us are watching the wrong part of it. We grew up measuring space races by firsts. First satellite, first human in orbit, first flag on the moon. That framing made sense in the 1960s, when the whole point was demonstrating national capability to a watching world. But what's running today operates on entirely different logic. Governments and private companies are laying down transportation networks, communications grids, and orbital infrastructure that simply didn't exist a decade ago. And alongside all of that, possibly the first genuinely functional off-world economy. So before the next major landing happens, it's worth asking, what exactly counts as winning when there's no single flag to plant? NASA spent roughly $25.4 billion in 1960s money to pull off Apollo. Adjust for inflation, and that number clears $250 billion today. Nearly everything came from inside the program itself. The Saturn V rocket, the Apollo spacecraft, ground systems, mission control, the works. And it delivered. 12 astronauts walked on the lunar surface across 6 missions. What we spend far less time talking about is what Apollo was never designed to produce. No transportation network came out of it, no logistics chain, no permanent infrastructure with a second act. The program proved we could reach the moon, and then the program ended. The Saturn V could haul roughly 140 metric tons to low Earth orbit and around 48 metric tons toward the moon. Extraordinary numbers for the era, but they belong to a machine built for a specific political moment. And once that moment passed, so did the machine. Artemis is working from a different foundation. The goal is a permanent, reusable transportation architecture. And honestly, that one shift in thinking is what separates this era from the last one.
I can still remember the emotions that I had on the moon, you know. I mean, we were 6 hours late landing, and we touched down and shut down, and man, here we are. We're on the moon, you know, you just excited. And
NASA is doing this for everybody in our country, and really for the whole world.
For the better part of 3 decades after Apollo, the urgency largely evaporated. Then China began assembling something worth watching closely. A lunar program built around sustained capability, executed mission by mission without dramatic pauses or pivots. Chang'e 4 landed on the far side of the moon in 2019, a first for any nation. Chang'e 5 returned lunar samples in 2020. Chang'e 6 completed the first far-side sample return in 2024. Chang'e 7 is targeting the lunar South Pole in the second half of 2026, specifically hunting for water ice. Look at that sequence, and the thing that jumps out is the consistency. No long gaps, no program resets, no years of political debate about whether to continue. The proposed International Lunar Research Station, developed with Russia and a growing list of partner nations, is aiming for a basic operational base near the South Pole by 2035. That region keeps drawing everyone back for the same reason. Permanently shadowed craters there may contain water ice in usable quantities, which would mean oxygen, drinking water, hydrogen, and rocket propellant accessible from the surface rather than launched from Earth at enormous cost. Nearby ridges sit in near constant sunlight, offering reliable solar power right next to craters where temperatures drop below 280 degrees Fahrenheit. Cold storage and available power in the same small patch of lunar geography. For anyone trying to run a long-term outpost, that particular combination is hard to find anywhere else on the moon. Every major program currently active American, Chinese, and European keeps arriving at the same conclusion about where to set up. A single crater near the South Pole may end up mattering more than any rocket sitting on any launch pad right now. NASA's architecture today looks fundamentally different from Apollo, and that's a deliberate choice. Through programs like Commercial Crew, the Commercial Lunar Payload Services Initiative, and the Human Landing System, NASA purchases capabilities from private companies rather than building every component internally. Private companies competing for contracts push hardware development faster, and the financial exposure sits with the companies taking on the contracts rather than entirely with the government. NASA buys the result. The hardware coming out of this model is already flying. SpaceX's Falcon 9 became the first orbital-class rocket to achieve routine reusability, and by 2026, it's surpassing 130 launches per year, most of them deploying Starlink satellites. Rocket Lab's Electron continues flying at a record pace, and its medium-lift Neutron vehicle is now targeting a debut no earlier than late 2026, after a tank test setback earlier in the year pushed the schedule back. Axiom Space is developing a commercial lunar spacesuit and working toward a private station in low Earth orbit. Apollo was built end-to-end by the government. Artemis relies on an ecosystem where private companies design and build the systems. Two different approaches, and the hardware coming out of each reflects that pretty clearly. What's also different is the pace. Government programs tend to move on government timelines. Companies burning their own capital and competing for the next contract tend to move faster, sometimes messily, but faster. Most coverage of the lunar architecture focuses on Starship, which makes sense given its scale, but the engineers working on the actual mission profile spend a serious amount of time on what has to happen before Starship ever reaches the moon: orbital refueling, and specifically, whether it can be made reliable enough to stake crewed missions on. NASA's Human Landing System plan calls for multiple tanker launches, cryogenic methane transfer, cryogenic oxygen transfer, propellant settling in microgravity, long-duration storage, and thermal management across the entire chain. Liquid oxygen needs to stay near negative 297 degrees Fahrenheit. Methane has to hold around 259. In space, heat leaks in constantly. Propellant boils off, pressure shifts, fluid moves in ways that gravity on Earth simply masks. Each of those problems gets harder when the goal is to do this repeatedly rather than once as a test. SpaceX has already transferred propellant between two tanks on a single Starship vehicle. A full ship-to-ship demonstration, with one vehicle launching as a target and a second docking with it weeks later, is on the schedule for sometime in 2026. NASA's estimates suggest roughly 10 tanker flights could be required to refuel a single Starship for one lunar landing, with some analyses running higher. Nobody has validated this at the scale a real crewed mission demands. Not yet, anyway. Getting to the moon is hard. Doing it repeatedly, on a schedule, with crews aboard, using a refueling chain nobody has fully tested at scale yet. That's the problem this decade actually has to solve. For most of space history, operating in orbit consumed capital without generating returns. Starlink has changed that, and the full weight of what that means hasn't really settled in yet across the industry. By early 2026, Starlink had crossed roughly 10 million paying subscribers across more than 150 countries. Analysts at Quilty Space project that figure could climb toward 17 million by year's end. Revenue estimates for 2026 run between $15 and $20 billion, and the segment now accounts for the majority of SpaceX's total revenue. A global communications network built on laser inter-satellite links and low-latency coverage, running as a profitable business. That's a genuinely new thing in the history of spaceflight, and it matters beyond SpaceX specifically because it proves the underlying model works. Orbital infrastructure can generate revenue at scale. That changes how investors, governments, and competing companies think about what's worth building next. Rocket Lab's Peter Beck has made a version of this point for years. Once launch gets routine enough and affordable enough, it quietly turns into something closer to freight, a means of moving things into orbit so other businesses can operate there. Railroads worked the same way. Once the tracks were down, supply chains formed, new towns appeared, and markets opened up in places that had been empty land a decade earlier. The infrastructure quietly became the point. We're somewhere in the early chapters of that same story, playing out a few hundred kilometers above our heads. Whoever ends up controlling the most pieces of the operational architecture shapes what everyone else can and can't do up there. That's what this race is actually about. Future lunar operations will need orbital refueling at scale, surface mobility, communications relays, cargo delivery, power generation, and resource extraction, all running together as one connected system, rather than isolated missions. A moon base near the South Pole, commercial stations in low Earth orbit. China's lunar program is advancing step by step. Starlink overhead is the communications layer underneath all of it. These systems are being built in parallel right now by different actors, with different timelines, and the programs that end up owning the critical connective nodes across that architecture hold a kind of leverage that planting a flag never produced. Apollo had a clean scoreboard. This doesn't. And the messiness of that is probably what makes it so hard to follow as a story, even though what's actually being built is larger in scale than anything the 1960s produced. Apollo answered one question about what we could pull off when the political stakes were high enough. The work happening now is trying to answer something harder and honestly less glamorous. Can we build the systems that make operating somewhere beyond Earth functional over a long stretch of time, not just once, but routinely? Transportation, communications, power, logistics, orbital refueling, and in situ resource use. Each piece is being developed right now by different teams with different timelines, and there is no guarantee that they all connect the way the diagrams suggest they will. Some of these programs will hit delays, some will get canceled, some will get replaced by something nobody has announced yet. That uncertainty is baked into the timeline, and anyone telling you they know exactly how this unfolds is working from the same incomplete picture we all are. When historians look back at this decade, the question probably won't be who landed first. It'll be who built the network that everyone else needed to function at all, and whether the people doing that work in 2026 had any real sense of what they were putting together. That foundation is being laid right now. We just can't see yet whose name ends up on it.